Hello and welcome to my math talk. My name is Sam Heidemann and today I'm going to be talking about Mersenne primes and perfect numbers. So a little background about what prime numbers are used for. Their primary use are for encryption. And this here is a diagram that outlines RSA encryption, which is kind of the foundation for modern encryption techniques. And the basis of it is you have two very large prime numbers, and when you multiply them together, you get a product. And that product is very hard to factor. The larger the prime numbers, the longer it takes to factor. So naturally, it's useful to have large prime numbers. And so that product is what goes into your public key. And then the person that you're sending it to has a private key, and they use it to decrypt your message. And the basis of this, as I said, is large prime numbers. So where do Mersenne primes and perfect numbers come from? Well, it started off uh, in the late 1600s. A French monk named Mersenne stated that numbers 2 to the n minus 1 were prime for this list of numbers here. This was kind of a tentative list that he was proposing. In reality, he was only really able to verify the first 5 or 6. After that point, it became much too large for the computation techniques that they had at the time. However, by 1947, Mersenne's range of numbers less than 258 had been completely checked, and the correct list was, as you can see down there, a little bit different. So he was wrong about some, he had missed some, but this was a more complete list of uh, ends for Mersenne primes less than 258. So that's kind of a history of Mersenne primes. So what exactly do I mean when I say Mersenne prime? So as Marion Mersenne proposed, when a number has the form 2 to the n minus 1, it is said to be, and is prime, it is said to be a Mersenne prime. So let's look at an example of this. So if we let n equal 3, we can see when we work that out, 2 to the third minus 1 is 8 minus 1, and that gives us 7. Since 7 is a small prime, we can quickly verify that it is indeed prime. The only divisors of 7 are 1 in itself. So from here, we can conclude that 7 is a Mersenne prime. From there, we need to know a little bit more about perfect numbers. So a positive integer n is called a perfect number if it is equal to the sum of all of its positive divisors, excluding itself in that divisor list. So another example here, we're going to let n equal 28. We know that the factors of 28 are 1, 2, 4, 7, 14, and 28. If we take out the 28 and sum them, we get, as you can see below, 7 plus 7 is 14, 14 plus 14 is 28. They sum to 28, and that is the anatomy of a perfect number. So since all of 28's factors add up to 28, we say that 28 is perfect. So we're going to talk about finding Mersenne primes now. They're kind of hard to find after you exhaust the first couple small ones that you can kind of check yourself, because primes are notoriously hard to find the larger they get, especially when they have to be of a certain form. So what we're going to talk about is a way to kind of simplify that process. So a theorem we have here, if 2 to the n minus 1 is prime, then n is prime. So this is kind of a restriction that we can place on our possible candidates for Mersenne primes to shorten the search. But to prove this theorem, we will be needing its contrapositive statement, which I stated below. If n is composite, then 2 to the n minus 1 is composite. So we're going to start with that first statement, if n is composite. So we're going to let n equal a times s, where a and s are between 2 and less than n for a natural number n. So we can see that if we break down 2 to the n minus 1, we can make it 2 to the a to the s minus 1. So we're going to consider a factorization of something of a similar form, and it's going to help us visualize some later steps. So if we take b to the s minus 1 for just a natural number b, we can factor it in a way so that we pull out a b minus 1, the base b minus 1, and then our exponents are going to be kind of distributed in the next factor, b to the s minus 1 plus b to the s minus 2. That continues until you get b to the s minus s, which is just b to the 0, which is 1. And this works if you just want to work it out in your head. You can multiply the first numbers, get b to the s, because b to the 1 times b to the s minus 1 is b to the s. And then every term after that is going to cancel with itself until you get minus 1 times 1. And that's where you get the minus 1. So that does factor out to b to the s minus 1. So using that same form, we're going to apply that to our 2 to the as, and we're going to see that if we take 2 to the a to the s minus 1, we can pull out a 2 to the a minus 1. And it's going to take that same form that we just saw with s minus 1 decreasing to s minus s, which is 0 in that factor. So from there, we can see that 2 to the a minus 1 does divide 2 to the as minus 1, which is equivalent to 2n, 2 to the n minus 1 by definition. And this means that 2 to the n minus 1 is composite, which was what we were trying to prove, if you can remember back to this slide. 2 to the n minus 1 is composite. So now that we've shown that by contraposition, since 2 to the n minus 1 is prime, then n must be prime. Okay, and here we're just going to look at the first couple of Mersenne primes that we know. This is the first 10 actually. So we have the exponents, we have the digits in the prime, and we have the digits in the perfect number. So you can see there's perfect numbers that are correlating with the same p exponent of Mersenne primes, and that's not a coincidence. That's definitely a relationship, and we're going to explore that later. You can see that the first 4 are just kind of common knowledge. They've been known for a long time and really have discoverers, but some of the larger ones were starting to come to light around the 1500s. You can see Euler even found one, a pretty large one. So an exponent of 31, which again is a prime number, as we just showed. All of those p exponent column numbers have to be prime. And you can see kind of how much they grow in size, from 6 digits to 10 digits to 19 digits to 27 digits. So they've taken a while to work out. All right, so now we're going to talk about that relationship that they have. So this theorem here states that a natural number n is an even perfect number if and only if n to the 2 to the a, n equals 2 to the a minus 1 times 2 to the a minus 1. For a prime number a, where 2 to the a minus 1 is the Mersenne prime form that we're familiar with by now. So in this example, we're going to just show how that theorem works. We're going to let a equal 3. And then from there, we see that, as we saw earlier, whenever the exponent is 3, we get a Mersenne prime of 7. And from there, we're going to plug that Mersenne prime into the rest of our formula there. And we're going to get, as you can see, 2 to the 3 minus 1 is 2 squared, which is equal to 4. So we have 7 and 4. 7 times 4 is 28. And if you can recall from our other example, we know that 28 is also prime. So this Mersenne prime 7 has a direct correlation with this perfect number 28. And from what we know, all Mersenne primes and perfect numbers have some relationship like this. And it's laid out by this formula here. So now we're going to prove that. So some things we need to know beforehand. Another way of defining a perfect number is the function sigma of n is equal to 2n, which means n's divisors summed are equal to 2n. That's what that function means. And that's basically our previous definition of a perfect number, except now we are including that number itself, and we're just saying that they sum to that number times 2, which makes sense because we're just adding another multiple of that number to itself. And then if n is an even integer, we can write n in this form, do the a minus 1 times m, where m is odd, and a is greater than or equal to 2 for our natural number a. And that seems a little arcane, but we're going to just be using that form later. So then we can write this function sigma of n in this form, 2 to the a minus 1 times sigma of m, using our definitions that we've laid out. So moving from here, we're going to go to the right first, supposing that n is perfect. So we're going to see, since n is perfect, we know that sigma of n is equal to 2n, and we're going to define some more variables here. We're going to let s equal sigma m minus m. So that's basically just the sum of m's divisors other than m, or subtracting m. And then we're going to let t basically just be our Mersenne prime of the form 2 to the a minus 1. Something to note, we know that t is greater than 1 since for our Mersenne primes a is greater than or equal to 2. So from here we can do a little bit of substitution and manipulation. We're going to bring back this form here of sigma n, right? 2 to a minus 1 times sigma m. And we're going to rewrite that because we have we've made variables to replace those expressions, t and s. If we add m to the other side of s, we get sigma of m is equal to s plus m. And that's what we get here on top of the first line. Sigma of n is equal to t times s plus n. So from there, we know that sigma n is equal to 2n. And we know that 2n is equal to, or n is equal to 2 to the a minus 1 times m. We substitute that in, we have an extra power of 2 hanging around, so that cancels out that to the minus 1 power. So we have 2 to the a m is equal to t times s plus m. And then we substitute t plus 1 in for 2 to the a by definition. Then we distribute and cancel like terms, and we're left with m equals ts. And this is basically, so suppose that s is greater than 1. That could be a possible scenario. So we know that s is less than m because t is larger than 1. So the product of t and s equaling m means that s is less than m. So that means 1 and s are distinct divisors of m other than m because of our definition of m, our definition of s, sorry. So s is equal to 1 plus s plus the other divisors, and that in itself is a contradiction. So that means that s has to be 1. If s has to be 1, this implies that sigma of m is equal to m plus 1, which makes m prime. Moreover, we see that m equaling ts, since s is equal to 1, we can substitute that in. We know that m is equal to t, which t was our variable for our Mersenne prime, 2 to the a minus 1. So not only is m prime, we now see that m is a Mersenne prime. So from here, we can see that by our definition of m, n is equal to 2 to the a minus 1 times 2a minus 1. And that is what we're trying to show. So that's the proof going in that direction. Coming back, it's a lot shorter. We're going to suppose that that expression is true. N is equal to 2 to the a minus 1 times 2 to the a minus 1, where 2 to the a minus 1 is a Mersenne prime. Then we're going to do some more manipulation here. Sigma of n is equal to this 2 to the a minus 1 plus 1 times 2 to the a minus 1. We're going to distribute that out, get to the a times to the a minus 1. And then we're going to pull a 2 from there because we want that to fit the form that we have for n. And now we see that we can substitute n in for this expression and get 2n, which shows, since sigma of n is equal to 2n, that shows that n is a perfect number and even at that. So in conclusion, we now know why large prime numbers are important. Besides from just being cool, prime numbers are used for RSA encryption. We know how to find Mersenne primes more easily. We know what Mersenne primes look like, right? And this theorem is just kind of reminding us that. We know there's a relationship between Mersenne primes and perfect numbers, a one-to-one relationship you can see below. So where do we go from here? Is there an odd perfect number? We don't know yet. Every perfect number we've found has been even, so we don't know. Are there infinitely many Mersenne primes? Like I said, we're just trying to find larger and larger Mersenne primes at this point. There's what currently going on, there's a movement called the Great Internet Mersenne Prime Search, and it's a bunch of people linking their computers together to just run calculations to just divide large numbers and see if they're prime, that have the right form. Right now, as it stands, we have 51 Mersenne primes and 51 corresponding perfect numbers. And the exponent of that 51st Mersenne prime is of around the size of 81 million. So it's something that looks like 2 to the 81 million minus 1. That's our 51st Mersenne prime. Yeah, it's a pretty big number. We found it in 2019, so that's a pretty recent discovery. And another thing that we don't know yet is, are there more double Mersenne primes? So the first couple ones that we know are double, right? They're just prime numbers that back to back are also Mersenne prime numbers. But it doesn't continue like that. We just know of a handful of these double Mersenne primes, but we don't know if they will continue along with the rest of the Mersenne primes. So that's just kind of where we are right now. These are my references. Thanks for tuning in.